Hello everyone, welcome to the third module of Statistics and Probability full course. My name is Sumit Shukla, a senior data scientist and an educator. In this particular video, we'll be talking about random variables and probability distributions. So let's get started. So now let's talk about distributions. What is distribution? So when we have a random variable, I hope you already know a random variable can be of two types, either discrete or continuous. So let's say I'm having a discrete random variable. And first of all, we are talking about the distributions for discrete. I will take an example for both and then we will talk in details about the variety of distributions we have. Distributions are very important and please listen to this topic very carefully. So when we talk about discrete random variable, discrete random variable, we know that the outcome can be discrete, it can be integer, right? So let's take one example. Let's take one experiment of toss of two coins, and I have taken this experiment for so many times, so you already know that the outcome can be head head, head tail, tail head, and tail tail, right? The random variable can be x can represents the number of heads, and it can be two head, one head, or zero head. Now if I plot this distribution, so I am having a plot. In the x-axis I'm having the random variable, and I already know this random variable can either take 2, 1, or 0. Here I'm having the count. So assume that you are performing this experiment of tossing two coins for many times, and you have noted down the number of times you obtained two heads, the number of times you obtained one head, the number of times you obtained let's say no head. So let's say I'm creating a table, and let's say so this is my trial number 1, so I'll write 1 over here. In the trial number 1 you obtained head head, so here I will write 2. In trial number 2 you obtained head tail, so 1. In trial number 3 you obtained tail head, so again 1. In trial number 4 you obtained tail tail, so again 0. In trial number 5 you obtained tail head, so 1. Trial number 6 you obtained tail head, again 1. 7 you obtained head tail, so 1. 8 you obtained head head, so 2. Then 9 you obtained tail tail, so 0. And 10 you obtain tail head, so again 1. Now this is my outcome or random variable x. Now I will just count and create a plot. So how many times I have obtained two heads? So 1 time, 2 time. So I'll assume that this is 1, this is 2, this is 3, and so on. So for 2 times I obtained head head, so I'll create a bar over here. Then how many times I obtained one head? So 1 time, 2 time, 3 time, 4 time, 5 time, 6 time. So 6 time, let's say it represents like this. And then how many times I obtained no head? So 1, 0, and 0, so 2 times. This is known as the distribution of discrete random variable, and we have a very good name for this distribution known as the PMF. This is PMF. This is known as the probability mass function. This is the probability mass function. Now please remember this, that if I'm tossing one coin, so let's say if I'm just tossing one coin, and we have already created this probability mass function. I hope you remember. I have shown you one website, seeingtheory.edu. In that website, you have seen that for the true probability, so the true probability of getting head and tail when you toss one coin is half and half, 1 divided by 2 and 1 divided by 2. So the probability of mass function of the true probability when you toss one coin will be 0.5, 0.5. So this is head, this is tail, 0.5, 0.5. But when you actually perform the experiment, this can change. This can be anything. This can be, let's say I'm having more head and less tail. So let's say this is 0.7, this is 0.3. When you tossed one coin for 10 times. So 7 times you obtain head, 3 times you obtain tail. Quite possible, right? This is known as the observed. This is known as observed. This is known as true. Similarly, for this example, the true, so what is the probability of getting 2 heads? It is 1 by 4. Probability of getting 1 head, it is 1 by 2. Probability of getting 0 head, it is 1 by 4. How? Because I have mapped them. Please remember, this probability is 1 by 4. Probability of 1 head will be 1 by 4 plus 1 by 4, which is 1 by 2. And this will be again 1 by 4. So the true PMF for this would look something like this, where this would be 1 by 4, which is 0.25, 0.5, and again 0.25. This is the probability PMF for my random variable x, which is a true probability. This is the PMF. This is for the discrete random variable. Now let's talk about the continuous random variable and how the distribution looks like. For continuous random variable, if you guys carefully try to understand the continuous random variable, we cannot have the discrete type values or integer values, but we can have range also. We can have range, right? For example, let's say the random variable is time an employee takes to commute between home and office. Now let's say we have defined the minimum and the maximum range. Let's say minimum the person takes 10 minutes, maximum the person takes 60 minutes. Now I can have endless possibilities between these two numbers, right? Let's say we have observed this. So let's say I have taken one employee, or let's say I have taken myself, and every day I'm just taking down the number of minutes I took. So let's create a table, let's create a set over here. This is my observed set for x. So x observed. The observed set for x is, let's say in the first day I took 11 minutes. Second day I took 32 minutes. Then let's say 23 minutes. Then let's say 59 minutes. Then let's say 43 minutes. Then let's say 29, 33, 48, 57, and 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For 10 days, I observed the number of minutes I took. Now, can I take each of them as a random variable? No, because this is a continuous random variable. So my question to all of you is that, are these the only possible outcomes which I can get from this experiment? No. We can have more outcomes. If I perform this experiment for another 10 days, I can get more values. Let's say someday I took 23 minutes 2 seconds, so 23.2. Let's say someday I took 11 minutes and 5 seconds. So there are endless possibilities. So I cannot take each entry or each outcome over here as one random variable. Then what is the solution? I would go with the range. So let's define the range over here. So range would be, let's say, from 10 to 15, 15 to 20, 20 to 25, 25 to 30, 30 to 35, 35 to 40, 40 to 45, 45 to 50, 50 to 55, and finally 55 to 60. And I will now just write down number of times I observed a value between this range or in this range. So let's write the count. So in between 10 to 15, I was having this value, which is 11 and 12. So I write 2 over here. Between 15 to 20, I don't have a value, 0. 20 to 25, 20 to 25, I'm having one value, so I'll write 1 over here. 25 to 30, 25 to 30, I'm having one value, so I'll write 1 over here. 30 to 35, so one value over here, one value over here, so two values. 35 to 40, 35 to 40, I don't see a value, so okay. 30 to 35, I was having no value, so I should write 0 over here. 30 to 35, I'm having 33 and 32, yeah, 2. So this was correct. Ignore if I'm doing something wrong because I'm just trying to quickly fill this table. 35 to 40, 0. 40 to 45, 40 to 45, one value over here, so 1. 45 to 50, one value over here. 50 to 55, I don't see a value. 50 to 50, 55 to 60, one value over here, one value over here, so two value. Now when I plot this, I will plot it as a range. So my x is over here, which is again the time taken by an employee to commute between office to home. Here I'm having the same count, but here I will have the range. So starting from 10, 15, 20, 25, 30, 35, 40, 45, and so on till 60. And then I will have this bars, which is known as the histogram. This is not the bar chart, this is the histogram. So 10 to 15, let's say 2, like this. Then 15 to 20, I'm having 0, so a line like this. Then 20 to 25, I'm having 1 and then 1. So let's say like this. And then again I'm having 2. And then again I'm having 0. Then again 1 and 1. And so on. Now this is basically my probability density function, PDF. Probability density function. Now why I'm calling it as a density? Because if I ask you what is the probability of a person takes the time between 10 to 15 minutes, I'm not talking about one point, I'm talking about a range, which is density. So that is the reason here the distribution is known as the density. And please remember, the probability of a one point in a continuous distribution or continuous random variable is always equal to 0. If I ask you what is the probability that a person will take 10 minutes, that would be 0. The probability is 0. The reason is we cannot calculate it. We cannot calculate it because the way we are calculating the continuous random variable is by using a measure. Here we are using a measure as the time taken by a person, right? And 10 minutes is something that a person can take endless number of time. So we don't know how many times a person can take 10 minutes divided by we know. So how many times a person can take 10 minutes? The probability of 10 minutes would be number of times the person takes 10 minutes divided by total time. So total time we know, total time is 60 minutes, but how many times the person has taken 10 minutes? I don't know. The answer, this can be infinity also, right? I don't know that. So the probability will end up becoming 0. So the probability of a point in a continuous random variable is 0. And the reason we call it as a probability density function is because we are not talking about one point probability, we are talking about a range. Now within discrete random variable, the distribution for discrete random variable and the distribution for continuous random variable, we have some very general distributions, some standard distributions that are very important in the field of statistics and probability. So that is what we are going to learn next. The various type of standard distribution that comes under both discrete and continuous. So we have talked about discrete random variable and continuous random variable. And we have seen a very simple example of how we can create distributions for discrete and continuous. Now there are some standard distributions that comes under discrete and continuous. So what we are going to do, we are going to talk about these standard distributions. So the very first, we will first talk about discrete. So within discrete, the discrete random variable, we have two very important distributions. One is known as Bernoulli and the second one is known as binomial. So Bernoulli distribution and binomial distribution. Now what is the Bernoulli distribution? Or we will first talk about the Bernoulli experiment. So when we talk about the Bernoulli experiment is a particular experiment in which, number one, the outcome is always binary. So the outcome is always binary, which basically means the outcome is either head or maybe win or loss, head or tail. So let's say head or tail, win or loss, or maybe 1 or 0. So it will always be binary. The second one is the number of trials is only 1. So we are just performing the experiment for one time. So the number of trials is only 1. So for example, let's say I'm having a coin and I tossed this coin for one time. So toss of this coin for one time. Now can I consider this as a Bernoulli experiment? Yes. Why? Because when I toss this coin, I may either get a head or a tail. So the outcome is binary. Now since the outcome is binary, this experiment is the Bernoulli trial. So why I'm calling it as a trial? Because I am performing the experiment for one time. So I can either get head or tail. So the Bernoulli distribution looks like very simple. We have already seen it, but I'm drawing it again. Let's X represent the number of heads when you toss a coin for one time. So you may either get a head. So let's say I obtained a head, and for tail it is nothing. So this is basically my Bernoulli distribution. Bernoulli distribution. Now please remember one thing, there is nothing difficult to remember about Bernoulli distribution. It is just a particular experiment which is having binary outcome and one trial. Binary outcome, one trial. Now binomial is something very much associated with Bernoulli. So when I perform the Bernoulli experiment for n number of times, then we get a binomial experiment. So what is binomial? Binomial experiment. So when the Bernoulli experiment is performed for n times, we get binomial experiment. We get binomial experiment. This is my binomial experiment. Let's take one example. Let's say I'm having a bag and we will try to understand the binomial experiment. So binomial experiment is nothing but when I am performing the Bernoulli experiment for n times, it becomes binomial. Again, the outcome of each trial in binomial experiment is binary. So again, assume that you are having a coin and you are tossing it for 10 times. So since I am tossing it for 10 times, it becomes binomial. But the outcome of each trial is going to be either head or tail, which is binary. And that is the reason it is a binomial experiment. So we have n Bernoulli experiments. When I combine them, it becomes binomial. Now let's understand how to calculate the probability of binomial experiment. So probability of binomial experiment. Okay. Now let's say I'm having a bag and this bag is having, let's say, 2 orange balls. So 2 orange balls. So let's say the bag is having 3 orange ball and 2 white balls. So 1 white ball, 2 white balls. So 3 orange and 2 white. Now my random variable x is the number of heads, my random variable x is the number of orange balls I may get out of this bag. Number of orange balls I may get out of this bag if the experiment is performed for 3 times. Now, if you are not able to understand it, let's try to take the example. So the experiment is, we have to take the ball out of the bag, note down the color. So what's the color? Orange. We will note it down and put the ball back to the bag. And I will do this for 3 times. Now, is this a Bernoulli trial? When I'm taking the ball out of the bag for 1 time, is it a Bernoulli trial? Yes. Why? Because I can either get a orange ball or not get a orange ball. So first time I obtained a orange ball. This is my one Bernoulli trial and I placed the ball back to the bag. Again I did the experiment. I obtained again a orange ball and I note down the color. I put the ball back to the bag and I did it again. I again take a ball out of the bag. It came out to be orange. I note the color and I put the ball back to the bag. Now what is happening? I have performed the Bernoulli experiment for 3 times. So each time I was taking the ball out of the bag, it was a Bernoulli trial. And I have performed the Bernoulli trial for 3 times. So let me just note down the outcomes. First of all, let me note down the experiment. The experiment is, take a ball out of the bag, then note down the color of the ball, and then put the ball back to the bag, back to the bag. Now we have to perform this experiment for 3 times. Now we have understood the experiment, right? Now let's say I'm interested in finding out the probability that I will get exactly 2 balls when I am performing this experiment for 3 times. So 2 orange balls in 3 trials. Now what are the possible combinations in which you can get 2 balls or 2 orange balls? Let's note it down. So this is my trial number 1, 2 and 3. Let's say for the first 2 trials I obtained orange. So let me write OO, and then you obtained a white ball. So white. Then for the first you obtained orange, then white, then orange. Then for the third you obtained white, then followed by orange and orange. So now these are the 3 possible combinations I may get out of this experiment. Now what is the experiment? I am taking a ball out of the bag, noting down the color, putting the ball back to the bag, performing this experiment for 3 times. My objective is to find out the probability that I will get 2 orange balls in 3 trials when I am performing this experiment for 3 times. These are the 3 possible combinations. Now if you carefully observe, each trial is independent of the other, because every time I'm taking a ball out of the bag is still having 5 balls, because we have total of 5 balls, right? So what is the probability of getting orange, orange, white? It will be simply probability of orange multiplied by probability of orange multiplied by probability of white. Similarly for this, orange, white, orange would be probability of orange multiplied by probability of white multiplied by probability of orange. Then white, orange, orange would be probability of white multiplied by probability of orange multiplied by probability of orange. Now probability of orange is 3 divided by 5. Probability of orange is 3 divided by 5. Probability of white ball is 2 divided by 5. So this will be 3 by 5 into 3 by 5 into 2 by 5. This will be 3 by 5 into 2 by 5 into 3 divided by 5, and this will be 2 by 5 into 3 by 5 into 3 by 5. So if you carefully observe, I can write each of them as 3 by 5 to the whole square into 2 by 5. I can even write this as 3 by 5 to the whole square into 2 by 5. I can write this as 3 by 5 to the whole square into 2 by 5. Now what is the probability of getting 2 orange ball in 3 trials? I am having 3 possible combination. So it can be either this or this or this. So when I am having an OR term, that basically means I have to add all of them, right? So it will be probability of O, white, which is plus probability of orange, white, orange, plus probability of white, orange, orange. Now we have already calculated everything. So it is, I'm just taking it over here. So it will be 3 by 5 to the whole square into 2 by 5 plus 3 by 5 to the whole square into 2 by 5 plus 3 by 5 to the whole square into 2 by 5. Now all the 3 terms are similar, so we can just simply write it as 3 times of 3 by 5 to the whole square into 2 by 5. Now this particular equation can be generalized for any binomial experiment. How? Let's see. The generalized equation is ncx px q to the power n minus x. This particular equation can get you the probability of any binomial experiment. What is n? N is the number of Bernoulli trials. X is the number of success in n trials. P is the probability of success, and Q is the probability of failure. So if I try to map this equation for this particular experiment, where I have calculated the probability is 3 times of 3 by 5 to the whole square into 2 by 5. Let's try to do it in next slide. So the formula is ncx px q to the power n minus x. Now, in the last experiment, we were performing the trials, Bernoulli trials, for 3 times. Here I have written it, right? So my value of n is 3. Now what is x? X is the number of success. Now if I consider getting an orange ball as a success, then I was interested in getting 2 orange balls, right? So my x is 2 because I am interested in getting 2 orange balls. Probability P is probability of success, which is nothing but probability of orange. And orange probability is 3 by 5. And Q is the probability of failure, which can be also written as 1 minus P. This is given as 2 by 5. Now if I put everything on the formula, this will be 3C2 3 by 5 to the 2 into 2 by 5 to the power of 3 minus 2, which is 1. The ncx factorial, this particular term can be expanded as n factorial upon x factorial, n minus x factorial. So 3c2 would be 3 factorial upon 2 factorial, 3 minus 2 factorial, which is 3 into 2 factorial divided by 2 factorial into 1 factorial. 2 factorial will cancel out 2, so we'll be left with 3. So 3 times of 3 by 5 to the whole square into 2 by 5. And here you can see we have already done this manually. So using this formula, you can find out the probability of the number of success in n Bernoulli trials. The number of success, which is x, in n Bernoulli trials, which becomes binomial, right? Let's take one more example, a quick example to help you understand this. So I'll just create a portion over here. So let's say there is a person who is trying to shoot a target. Here we have a person. This person is trying to shoot a target for 10 times. For 10 times. So n is 10. Now, is this particular experiment consist of a Bernoulli trial? Yes, because when the person is trying to shoot the target, it will either hit or miss. So it is a binary experiment, which is the outcome is binary. And if I consider the experiment to be performed for 1 time, it is a Bernoulli trial. Since I am performing this experiment for 10 times, it becomes binomial experiment. So let's say the person is trying to hit the target for 10 times. The probability that he will make a hit is let's say 0.4. So there are 40% chances that if a person try to make a hit to the target, it will hit the target 40% of the time. So the probability of miss will be 0.6, right? Now I'm interested in probability that he hits the target exactly for 5 times. So I'm interested in 5 success in 10 Bernoulli trials. So my x value will be 5. I quickly apply the formula n cx px q to the power n minus x. N is 10, c 5. Probability of hit is 0.4 to the power 5 and then 0.6 to the power of 5. You can solve this and you will get your answer. What is the probability that if the person is trying to hit the target for 10 times, he will make a hit, he will make an exact hit for 5 times, and this will be your probability. This is the binomial probability. Now, if I calculate all the probability for all the random variables, in this case, in the case of hitting the target, what is my random variable? My random variable x is the number of times this person makes a hit. Now the person can make a hit for all the 10 times, for 9 times, for 8 times, for 7 times, 6 times, or maybe for 0 times. So these are all the random variables. Now against each random variable, if I calculate the probability and I plot them, so let's say here I am having x, here I am having probability of x is equal to xi, and if I calculate all the probability, what is the probability that he will hit the target for exactly 10 times, for 9 times, for 8 times, for 7 times, and so on. And if I plot it in a mass function, so here I'm having x, here I'm having, let's say, probability p of x is equal to xi, then this will become my, this will basically become my PMF of binomial probability or binomial experiment. I hope everyone is clear about this. We can have a quick Excel example to demonstrate you how this particular PMF looks like. So let's look at an Excel example. Now here I'm having an Excel worksheet. Let's say this is my x, which can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What is the meaning of 0? That basically means a person was not able to make any correct hit. So if the person was trying for 10 times, he was not able to hit for any time. The number of successful hits was 0. What is the meaning of 1? 1 basically means when the person was trying to hit for 10 times or maybe shooting for 10 times, he was able to hit the target only for 1 time. So that's what my x is. I'm now interested in calculating the probability of x is equal to xi. So let's do that. We will use the formula, the combination formula. So combine is the function that we have in Excel, and the total number of trials are 10. X is this multiplied by, so NCX, probability of success was 0.4 to the power of x, 0.4 to the power of x, and I will put this in a bracket so that nothing is getting wrong, and this is multiplied by failure, so q, so 0.6 to the power of n minus x, so 10 minus x, and I close the bracket and I think everything is fine. Let's expand this formula. I have the probabilities. Now let's plot it. So I'll go to insert. I'll choose a chart, maybe a column chart. And here we have the probability, which is wrong. Actually, it is plotted very wrong. I should choose only, I think if I choose this also. let me try it for one more time, otherwise we have to manually do it. Okay, it is not coming correctly, so let's choose only this one. Insert and this chart. Now here, first of all, this is not 1, this will be 0, this will be 1 because we haven't selected the x. So assume this is 0, then this is 1 and so on. Now you can see that the probability that a person will hit for 4 times is highest. 4 times is highest, and here you can see in the result also that the person hitting the target for 4 times is highest, and then as we move forward it becomes lower and lower and lower, and if I go below 4 it is becoming lower and lower and lower. So using the probability mass function of any discrete random variable, we can answer a lot of questions. So if I ask you, what is the probability that the person will be able to hit, or the person will be able to make at least 5 correct hits, or at least 5 successful hits? So at least 5 means I am interested in the probability of x greater than or equal to 5, which basically means I'll just simply take the summation of all these probabilities, which is equal to 0.36. So there are 36% chances that the person will hit at least for 5 times. What is the probability that the person will be able to make the correct hit at most 5 times? At most means less than or equal to 5, which basically means I am interested in all these probabilities, which is 83%, which basically means the person will be able to make at most 5 correct hits 83% of the time, right? Now using this PMF of various distribution, various discrete random variables, we can answer a lot of questions, right? And that is the reason these distributions are created. But we are interested in one such distribution, that is I would say that is a very important distribution in the entire statistics and entire machine learning. That is known as the normal distribution, which comes under the continuous random variable. So we have completed a discussion around discrete random variable, under which we talked about Bernoulli experiment and the Bernoulli distribution, then binomial experiment and the binomial distribution, and this is the binomial distribution. Now let's talk about the continuous random variable, and within that the most important distribution is normal distribution. If you guys are targeting for any data science job and you have to attend your interview for the data science field, then this topic is one such topic that you will 100% find out in your interview. It can be in any way, but it will be around this topic. So please listen to me very carefully, because this is really important when it comes to data science interviews. So when it comes to continuous random variable, we have a distribution known as the normal distribution. And normal distribution is something that looks like a bell-shaped curve, something like this. Now, what is the meaning of this? So if I assume that the x-axis represents income and the y-axis represents the count or the probability, then within this range, I have highest number or the highest occurrence of the observations. So I have maximum number of people in the mid range, in the mid income range. This is known as the center of my distribution. Now, what I have drawn right now is a normal distribution, but in reality, normal distributions can be of variety of shapes. As of now, you can see it is a very symmetrical shape, but in reality, you might get a very symmetrical shape of a normal distribution, or you might not get. So in order to understand whether your data is following a normal distribution or not, we have something known as the standard normal distribution. Now, why we have a standard normal distribution? A standard normal distribution will help you to compare few properties in your original data. So let's first of all understand what is a standard normal distribution, what are the properties of standard normal distribution, and then we will try to compare our data with the standard normal distribution to generate some insights. Let's try to understand the standard normal distribution. Now here I am having a particular standard normal distribution. The advantage of standard normal distribution is that it is perfectly symmetrical, which basically means this is my center, which basically means this is having the mean, this is my mean point. So mean, median, and mode, all the three quantities fall in the center. I'm having 50% data below this, 50% data above this. So it is perfectly symmetrical. Half here in the left side, half here in the right side. Now, the numbers you look into the x-axis are known as the z-scale. We will talk more about it. Don't worry, I will explain you everything. What is z-scale, how we got these numbers, don't worry. As of now, just try to understand what is a standard normal distribution. So number one is the mean and the median and the mode, all these three properties lies in the center. It is perfectly symmetrical, 50% on the left, 50% on the right, which basically means 50% data is on the left, 50% data is on the right. According to the standard normal distribution property, 68% of the data lies between plus minus 1 standard deviation. 95% data lies between plus minus 2 standard deviation. And 99.7% data lies between plus minus 3 standard deviation. Now what is this? This is 1 standard deviation. 1 standard deviation below, 1 standard deviation above. So between these 2 points, I am having 68% of the data. Between these 2 points, I am having 95% of the data, and between these 2 points, from this point till this point, I am having 99.7% data. If you are not able to understand how I obtained this z-scale and what I am talking about 68, 95, 97, let's try to understand it with a real example. First of all, let's try to understand the z-scale. So what is z-scale? For this, we have to jump into the topic of scaling. Now, don't worry. We have a topic which we are talking about, which is normal distributions. We have talked about standard normal distribution. We have looked into some of the properties, but there is one confusion. The confusion is what is z-scale and how we have obtained these numbers. And what is 1 standard deviation below, 1 standard deviation above. So we will pause this topic as of now. Just create a barrier over here. We'll try to understand this small topic, which is scaling and the z-scale. Once we are clear with this, then we will bind everything and you will be very much clear. So stay with me for another 10 minutes and you will be clear with everything. So what is scaling? Now the problem is, let's say I'm having 2 variables, age and income. Let's say age is, a person is having age of 27 and income of $1,000, something like that. Now can I compare these 2 values? Can I say this is a very low value and this is a very high value? No, essentially we cannot. Why? Because both of them are having a different scale. Age is in the scale of year, while income is in the scale of dollars. So I cannot compare these two values. They belong to two different scales and we cannot compare them, right? But what if I want to compare them? Then we have to make them into a common scale, right? And that is what scaling is known as. So scaling is a process of converting the data into one common scale using which I can compare various values. There are two common approach which we follow in scaling. One is known as the min-max scaling, also known as the normalization scaling. The second one is known as the standardization or the z-scaling. The z-scaling. In the min-max scaling, I try to convert the complete data into a scale of 0 to 1, where minimum is 0, maximum is 1. The formula is very simple, x minus min divided by max minus min. I'll show you the example in Excel. As of now, just look into the formula where x is the value I want to convert. So x is the value we want to transform or convert. Now here in z scaling, the formula is x minus standard deviation, x minus mean divided by sigma. What is x? X is the value we want to convert. Mu is the mean of the column, mean of the variable, and sigma is the standard deviation of the variable. So we have this formula. Now let's try to apply this formula in actual data in the Excel file to make sense out of it. And then you guys will be very clear about how we obtained this y-axis. This is the major question, right? We have the normal distribution, standard normal distribution topic parked as of now. We are trying to understand scaling. And the main question that we are trying to answer right now is how this z-scale came into picture. And once we are clear with this, then this standard normal distribution will make more sense to you, right? So keep this topic parked. We are talking about this topic and now we are moving forward to understand the scaling topic in Excel with particularly a data example. So let's do this. Now here you can see we have a data which is having age, BMI, and charges, the insurance charges. I cannot say that this value is very low, this value is middle, and this value is very, very, very high. Why? Because age is in year, BMI is in kg per meter square. If you know, BMI unit is kg per meter square, and charges are in dollars. These all three are in different scale. I cannot compare them, right? Let's try to use min-max scaling. So for min-max scaling, I need the minimum value. So let me insert quickly some rows. So let's say here I'm having minimum, maximum. So I'm just calculating the minimum for age. Is equal to minimum of the column age. So I'm having the minimum value to be 18. Then calculate the maximum of the column age. The maximum value is 64. Similarly, I'll call this column as age underscore normal. Similarly, I'll do it for BMI, BMI underscore normal, and then for charges, charge underscore n. I'll just find out the so let's quickly do one thing. Let's shift these columns. And let's shift this column also. so that I can simply just extend the formula and I do not have to write it again and again. Now if I just simply extend this formula, I'll get the minimum of age, BMI and charges, and this will give me the maximum of age, BMI and charges, because age, BMI and charges are one after the other. So I just extended the formula, right? Now let's apply the formula is equal to x, which is this value I want to convert, minus minimum. So I'll just freeze this value. So I will put a dollar x minus min divided by the value max and then minus and then min, and I will, so let's do one thing, let's not freeze I, so that if I extend the formula this is not getting fixated. I'll just fix the row $4 and $3 and let's enter. Let's try to apply it on the entire column and let's try to extend it to BMI and charges also, and let's try to extend it to all the rows. Now all these three columns are in a scale where minimum is 0, maximum is 1. So assume that you have a number line, minimum is 0, maximum is 1. Now the middle point will be 0.5. So the mean is 0.5. So any value which is close to 0, you can assume that the value is very low. Any value which is close to 1, you can assume that the value is very high. Any value which is around 0.5 is the average value, right? Now the scale is very clean. And all these three columns, age, BMI and charges, are now in this scale, the normalized scale. Let's try to compare the value. If I look at this person, the age of this person is 0, which basically means this person is the person who is having the lowest age in my data. The age 0 means the person is having the lowest age, the minimum age. Then 0.47 is the BMI, which basically means the BMI is around mean. As I told you, 0.5 is the middle, 0.47 is near to 0.5, right? So BMI is around average, while the charges are 0.009, which is very close to 0, right? So what I can conclude for this person is a young person, very young, having average BMI and very low charges, right? Let's take one more person. Let's say this person. The age is 0.91, which is close to 1, right? 0.91 is close to 1. So age is 0.91, BMI is 0.26, close to 1, 0.1, so 0.26. And then charges are 0.4, which is close to the middle value. So if I talk about this person is having very high age, not very high BMI. So BMI is below average, but charges are around average, right? Let's talk about a person who can be a outlier or something. Let's see if I can find out some interesting value so that it makes some real sense. Okay, if I look at this person is having 0.5 as age, middle age. The BMI is for this person is below average, but the charges are very high for this person. You can see this person, right? So I hope now you guys are able to understand how to read values in a normal scale. Now normal means minimum is 0, maximum is 1, and the formula is x minus min divided by max minus min. In the Z scaling, which is standardization, we need the average, we need the standard deviation. And once I do this, let's do this first of all. So this will be my age hyphen z, and this will be my BMI hyphen z, and then charges hyphen z. Now let's apply the formula is equal to, so first of all we have to calculate the mean, so is equal to average. I need average of the age column. I will just extend this formula to the next cell, next two cells. Then I need the standard deviation, so I'll just use this standard deviation of the BMI age column. Then I will extend this to the next cell, and now we will apply the formula is equal to x minus mean, so x minus mean, and I will again just freeze the row x minus mean divided by standard deviation. This is my standard deviation. I will freeze the row and enter. Now let's extend it to all the rows. I don't know why it's not happening. Let me try it one more time. Okay, I don't know why it's not happening, so I have to do it manually. And then I will extend this formula to the next column also. So let's do it like this. And this one also. Okay. Now in the Z scale, in the Z scaling, my middle point is 0. Then I'm having -1, -2 over here, +1, +2, and +3 over here, and -3 over here. What is these value? What are these values? These are known as my standard deviation. This is my mean. So standardization or Z scaling will convert your data in such a way that now the data is having a mean of 0 and the standard deviation of 1. So if you get a value close to 0, that basically means you are in average. If you go on the positive side, you are moving above average, and the higher you move, that many standard deviations you are above the average. So if let's say the value is plus 1.2, which basically means you are one standard deviation above the average. If let's say the value is -3, that basically means you are 3 standard deviations below the average. So Z scaling will convert your complete data into a scale where the center becomes 0, the mean becomes 0, and the standard deviation becomes 1 unit on either side. For min-max scaling, it was something like this: 0, 1, and middle is 0.5, right? Let's quickly compare it and try to check the Z scale. So here, if I look into this person is having BMI of 0.5. 0.5 means very close to 0, right? So 0 is the middle, 0.5 is very close to 0. Then -1.5 is the age, which basically means from 0, the person is 1.5 standard deviation below the mean. Then -0.9 charges. From the mean, the person is 0.9 standard deviation below the mean. So this person is having normal BMI because the value is close to 0, very low age, and very low charges because both the values are on the negative side. So you can see that with standardization, since I'm having positive negative sign and middle is 0, it becomes very easy for interpretation. If the value is positive, I know this is above average. If the value is negative, I know this is below average. The value is positive, which basically means it is close to 0. That is the advantage of standardization. Now this is the z-scale which you guys can find out in my standard normal distribution. So if I go back to my standard normal distribution, this is what the z-scale is. So the middle is 0. I have one standard deviation below the mean, one standard deviation above the mean, and so on. Now according to the property of a standard normal distribution, it states that 68% of the data is plus minus 1 standard deviation above or below the mean. 95% data is plus minus 2 standard deviation. 99.7% data is plus minus 3 standard deviation. Let's try to quickly prove it. Let me prove it. For that, first of all, we have to check which particular column among age, BMI and charges follow normal distribution. So I already know that BMI follows a normal distribution, which basically mean when I plot it, it would resemble a normal curve, a bell-shaped curve, which is symmetrical. You will get half data from below the center and half data above the center. And since I have converted the BMI column completely into a z-scale or standard scale, now just see the magic. I have selected the BMI column, and now we will go to the insert option in this Google Sheets, go to chart, and we will select the histogram. Now if you closely observe this histogram, you can see that this point is the center. 0.03 is the center, and below this value I am having negative points. Above this value I am having positive points. Now you can see that the data is spread around minus 2 standard deviation, which basically means below it is distributed 2 standard deviation below the mean and 4 standard deviations above the mean. Now you can see that it is not perfectly distributed. 2 standard deviation below, 4 standard deviation above. So here I am having less data, here I am having more data, or the spread is more on this side, the positive side. So this is one thing which can understand. This is a normal distribution, but this is not standard normal. So in order to compare this distribution with something, we need a standard thing, right? Let's say if I have to compare my performance in any exam, I need some standard score, right? Standard score is 100. So maximum is 100. The best is 100. So whenever we try to compare something, we need a standard, right? Similarly, in order to compare the distribution of a continuous random variable which appears to be normal, I need a standard normal distribution, and this is where my standard normal distribution comes into picture. This is my standard normal distribution. Now standard normal distribution says that your mean, median and mode will lie in the center. And if it is not lying in the center, if your mean is not equal to mode, is not equal to median, your distribution is not standard normal distribution. It will be either left skewed or right skewed. These are the two terms which I am introducing. I will explain you as we move forward, don't worry. But as of now, we are trying to understand the properties of normal distribution. And here I have already written the 3 properties, which is 68% of the data lies across plus minus 1 standard deviation above or below the mean. Similarly, 95% 2 standard deviation above or below the mean, and 99.7% data lies across plus minus 3 standard deviation, right? Now what we are going to do, we are going to quickly prove it. So here we have the data. I'll just quickly close this. I'll copy this data into a new sheet over here. Now we will calculate the mean, median and mode. And for simplicity purpose, let's not use the z-scale, let's use the original scale so that you guys are able to understand this. So I'll just replace this column with the original data, BMI. What is the average BMI is equal to average of this column what is the median. So median, median of this column, and what is the mode, mode, mode of this column. And here we have, so now you can see that mean is 30.6, median is 30.4, mode is 32.3. These values are approximately close to each other, not exactly same. So first impression about this distribution is that it is not standard normal distribution, but it's something close to standard, right? But how much close? Let's try to understand that. First, we will prove the property. The property is that 68% of the data falls across plus minus 1 standard deviation, right? So let's quickly find out the standard deviation. So STD DEF is equal to STD. So this is my standard deviation of this data. It is 6.09 standard deviation. If I go plus 1 standard deviation below the mean, so let me create a table over here. 68%. I go, so this is my mean minus let's say this is my lower limit, this is my upper limit. I'll explain you everything, don't worry, don't get overwhelmed. And this is my count, this is my total, and let's write 68% over here, and this is mean, so 1 standard deviation. So now what we are going to do, we are going to take mean and subtract 1 standard deviation. So 1 standard deviation, so mean minus 1 standard deviation. The lower limit is 24.5, then mean plus 1 standard deviation. The upper limit is 36. Now I will count how many values are falling in this range, because my objective is to find out the percentage. So I'll quickly apply a filter over here, and I will create a filter by condition, and my condition is between the lower value is 24.5 and upper limit is 36.7, and I'll just quickly create a filter. Now I'll just simply count it. If you carefully look over here, the count is 900. So there are 900 values that falls in this range. What are the total number of values? For that I have to remove this filter. So I'll say none, I'll say okay, and I will calculate. So 1338 is my total. So 1338. Now let's calculate the percentage. Percentage. So my percentage is equal to count divided by total, and this is 0.67. If I convert this into percentage, it is 67.2%. The standard value is 68%. My data is resulting in 67.2%. This is the first proof of the first property. The first property says that 68% data lies between plus minus 1 standard deviation. I am getting 67.2 because it is not standard normal, right? The second property is 95%. So 95% data lies between plus minus 2 standard deviation. Let's check the lower limit. So is equal to mean minus 2 times of the standard deviation, then is equal to mean plus 2 times of standard deviation. And now I will count. So I will go over here. My condition is between, my lower limit is 18.4, upper limit is 42.8. I'll click OK, and I will now count. The count is 1281 data points. 1281 81. So let's quickly write it down over here. 1281, 1338 is my total. I'll just extend this formula to the next, the below cell, 95.74. What is the standard value? 95%. What I am able to achieve? 95.74. Why there is a difference? Because BMI is not my standard normal distribution. According to the standard normal distribution, around 95% values in my data point will lie between plus minus 2 standard deviation, and here you can see final one is 99.7% of my data falls between plus minus 3 standard deviation. So is equal to mean minus 3 times of standard deviation is equal to mean plus 3 times of standard deviation. Now I'll calculate how many data points I'm having in this range. So 12.3 to 48.9, and I'll click OK. I'll just quickly count. It is 1334 and total is 1338. So 1334, this is 1338, and I will extend this formula to the next row, and I'm getting 99.7, which is exactly the same, right? So this is the proof of these three properties, that 68% of the data lies between plus minus 1 standard deviation, 95% plus minus 2 standard deviation, 99.7 in plus minus 3 standard deviation. Now, if I am given with a particular value, so let's say I'm given with a particular value, how I can find out that what is the probability at that point? If you're not able to understand my question, don't worry at all. Let me try to make you understand what I'm asking you. This is my standard normal distribution. This is my middle point, which is 0. 0 means the mean is 0. What is the probability that a data point will lie below this point? What is the probability? It is 0.5, and above this point it is 0.5, because as you already know that if I'm having if I consider the complete probability, so what is the probability that a data point will lie anywhere in this particular range? It is 1, right? We know the minimum range, we know the maximum range. I know the probability that my data will lie somewhere in the middle, so I know it is going to be 1. What is the probability that it will lie below mean? 50%, above mean 50%, if it is a standard normal distribution. So in order to find out the probability at any point from the left, we have something known as a z-table. Z-table is basically a standard normal distribution table, a standard normal distribution table, which helps us to find out the cumulative probability from lower point to this point. If I ask you what is the probability that a data point will lie below this point, so using the z value, so let's say the z values over here is -1. So using the z table, we can find out this probability, which is the area under the curve. Now let's see one example. Let's say a set of biology marks in a class are normally distributed with a mean of 70 and standard deviation of 6. Standard deviation of 6 points. Now let x represents the score on randomly selected person. So let X represents the score of a randomly selected student. Then what is the probability that the marks of this student would be between 64 to 79? Now this question is very simple to solve. We just need the properties that we have learned. Let's create the normal distribution first of all. This is my normal distribution. The mean is 70. Standard deviation is 6, which basically means I'll go one standard deviation below, so I'll get 64, one standard deviation above, so I'll get 76. 2 standard deviation below, 58. 2 standard deviation above, 82. Now what I need the probability between 64, which is this point, 64, which is this point, to 79, which is between 76 and 82, right? So from 76, if I go half standard deviation above, this will be 79, right? So this is the area which I'm looking to find out. Let me just highlight the area. This is what I'm looking to find out. I hope you guys are able to look at the area. It looks like I'm coloring a book, but I hope this makes sense. Now this is the area which I'm interested in. Now if I go with the logic and the properties that we have learned, so from this point till this point, my the percentage of data points, or the probability of a data point between 64 to 76 is 0.68, 68%. We know the property, right? Now from this point till this point, from this point till this point, and from this point till this point, what is the area under the curve? So if this is 68, then this point will be, or let's not look at the complete curve. Let's look at the middle portion only. So from 58 to 82, from 58 to 82, so probability of data point between from 58 to 82 is 0.95, 95%, right? If I subtract this middle portion, this point, I will get this portion and this portion, and I need the half of this portion, right? As we know that this part and this part is going to be exactly the same, right? So let's call this as C, and let's call this as C. Let's say 0.68 plus 2C is equal to 0.95. So 2C is equal to 0.95 minus 0.68. C is equal to 0.95 minus 0.68 divided by 2. This will give me C, this part, right? So let's calculate C. So this will be 0.135. Now I am interested in half of it, right? So my final answer will be probability of a data point between 64 to 79. I'm interested in this point, will be 68, which is 0.68 plus 0.135 divided by 2. So 0.68 plus 0.675, which is 0.7475. This is my final answer. So there are 74.7% chances that a person who is randomly selected in the class will have the marks between 64 to 79. Now in order to solve this question, we have used just the property of a normal distribution, which states that 68% of the data lie between plus minus 1 standard deviation, 95% between plus minus 2, and 99.7% plus minus 3. I hope this is making sense, right? Now let's take one example which will utilize the Z table, for which in order to solve this we need the Z table. So the question says the scores of ZMAT or GAMT, ZMAT are roughly normally distributed with a mean of 527 and a standard deviation of 112. What is the probability that of an individual is scoring above 500? So my first question is probability of an individual is scoring above 500. Now in the previous question we were able to solve it because the numbers that was given in our question was in the terms of n standard deviation. So the standard deviation was 6 units. I was given the minimum and the maximum range in such a way that I was able to make calculations. I was able to use elementary math to get to the point, right? But now we are not able to adjust it because 500 and then standard deviation is 112. It is really difficult to use the logic and use elementary math to get it done. In this case, Z tables are very useful. Let's solve this question. I know that the ZMAT scores are normally distributed with the mean, which is 527, and standard deviation is 112. Now I will find out how many standard deviation above or below this value is lying at. So we'll use the standardization formula. We will find out the corresponding Z value, which is nothing but x minus mean divided by sigma. X is 500, the value to be scaled, minus mean 527 divided by 112, which will be minus 0.24. So if I consider the Z scale, this value will be 0 and minus 0.24 is over here below mean, minus 2.24. Now what is the probability that the person will be able to score above 500? In which area I'm interested in? So if this point is minus 0.24, then I'm interested in the area above this, which is this area. The probability that the person will be able to score above 500. So I'm interested in this area, this particular area. Now how we will find it out? So using the Z table will provide me the area under the curve from this point all the way up to this point. Remember, AUC that you will get from the Z table will always be from the left. So once I have the area, which is the probability from this point all the way up to this point, I'll subtract it from 1 and I'll get my required answer. Let's check the Z table. Now here we have the Z table, and if you read, this is the standard normal distribution. Table value represents area to the left of the Z score. So if this is my Z score, left of the Z score. I'm interested in the value which is minus 0 point. So let me just cross check it. Minus 0.24. Let's check the area under the curve. So minus, this is 0.2. So we have to first read the row and then the column. So minus 0.2 and then 4, this value over here. So minus 0.24. The intersection of these two values will lie over here, I think. Yes. So this is 0.40517. 0.40517. So this x is 0.40517. I'm interested in this. So what it will be is equal to 1 minus probability of x less than or equal to 500, which is 1 minus probability of 0.40517. The answer will be 0.59. There are 59% chances. Let's say there is one more question in the same example. How much minimum marks should the individual score in order to be in the top 5%? Now this is a very interesting question, and if you guys can understand it, you have understood the complete normal distribution. Top 5%. If this is my middle value, top 5% means below me or below that point 95% data is there. So if I draw the normal distribution and below, so let's say this is the point which I want to find out, and below this point I'm having 95% of my data, right? So I know that I want to find out that z value, x minus mu divided by sigma. I need to find out that x where the z value is this. So what is the z value at 95%? Let's look into that. The z value at 0.95. So I have to look at the area now to find out the z value. So 9505 is over here. This is 1.6 and 5. So 1.65 is my z value. So the z value over here is plus 1.65. So I know the z value plus 1.65 is equal to x minus mean is 527 divided by standard deviation is 112. Again the elementary math, 1.65 multiplied by 112 is equal to x minus 527. So my x will be 1.65 multiplied by 112 plus 527, and this would be 710.6, which basically mean the person has to score a minimum of 710.6 so that the person can lie in the top 5%, and below that person I am having 95% of the observations. Now this is the application of z-table. How z-table can help you to find out the z values, and how z-table can help you to find out the area under the curve, which is essentially the probability. What is the probability that I will have a data point below this point, below this z value? That's what the application of z-table is. Now we have learnt about a lot about standard normal distribution, right? Now what we are going to do, we are going to learn last property of standard normal distribution, which is the analysis of skewness. We know that a standard normal distribution looks something like this. A bell-shaped curve which is symmetrical, which basically means 50% data below mean, 50% data above mean. But this is standard, and in reality it is very difficult or close to impossible to find out a random variable, a continuous random variable which appears to be a standard normal distribution. So we use standard normal distribution as a benchmark, but in reality you may get a distribution which is either left skewed, right skewed, or no skewness or near skewness. Let's look at all the three types. This is known as the left skewness. I apologize, this is known as the right skewness. Right skew. Why I'm calling it as right skew? because the skewness is on the right side. So right skew. In the case of right skewness, this tail happens to be because of the presence of outliers. The presence of outliers. Presence of outliers. While most of my data is on the lower side. So here I will get the mode followed by the median, and then I will have the mean. So I hope you guys remember that when we were talking about the descriptive statistics, we have learned that if I'm having outliers on the higher side, my mean will shift to the higher end. And that is the reason you can see that the mean has shifted to the outliers or towards the outlier. Now below this point, below the median, I will have the 50% of my data, and above this I will have 50% of my data. This is known as right skewness. I can also get a distribution which is left skewed, something like this. Now here again, you guys can easily understand this tail is because of the presence of outliers. Presence of outliers. And then again, this is the mode. The mode. We have the median somewhere around here. And finally the mean. So mean again shifted towards the outlier. Now here most of my data is on the higher side. If I consider this x-axis to be my income, then this left side graph represents that most of the people are having low income, while in the left skewed graph or left skewed distribution, we can understand that most of the people are having high income, but due to the presence of few people who are having low income or very low income, the graph has been, or the distribution has been skewed, and we obtained a left skewed graph. Now in the case of right skewness, my mean is greater than median is greater than mode. This represents the presence of right skewness. In the left skewness, my mode is greater than median is greater than mean. This is the presence of left skewness. And in the case of no skewness, mean will be equal to or approximately equal to median, will be equal to or approximately equal to mode. If you are getting something like this, you can say your distribution is close to normal distribution. Close to normal distribution. Now please remember the properties that we have learned, 68%, 95%, 99.7%, which is also known as 1, 2, 3 rule. It will be best applicable if your distribution is close to normal distribution. While if your distribution is having left skewness, right skewness, well, those properties will not be 100% true. It will be close. It will be very close. Sometimes it will be very different. So whenever you are applying the property, please make sure that your distribution is close to normal distribution. The example of BMI that we have seen was close to normal distribution, and we can just go back to the same sheet. So let me go back to the same sheet. Here we have the data, and here you can see that the mean, median and mode were very close to each other. So this distribution was close to normal. It was not perfectly normal, it was close to normal, and that is the reason these properties hold true. Otherwise, if this distribution was not normal, these properties would not have held true. I hope this makes sense. So we have covered a lot of topics, and the most important topic that we have covered till this point was the normal distribution, the analysis of z-table, how to read a z-table, how to make use of z-table to find out the probability values. And we have also learned about descriptive statistics and a bunch of probability the random variables, continuous, expected value. We have learned a lot, right? Now we are going to start with the second very important topic under our statistics and probability framework, which is inferential statistics. I have already given you the essence of what inferential statistics is and why we need it when we were discussing about descriptive statistics. But now we are going to understand it completely, and also we are going to utilize the power of inferential statistics to make estimations. So let's start our discussion. So when we talk about inferential statistics, in order to understand inferential statistics, we will take one example. Let's say you work for a marketing company. And your manager wants you to find out on an average how many recharge, or maybe the average recharge. So your manager wants you to find out the average internet recharge, the average internet recharge made by the Indians. So I'm talking about the complete Indians in last year. Now just look at the scope of the problem. We are talking about complete India, and your task is to find out the average internet recharge that was done by complete Indians in last year. It's a very big challenging problem, right? So let's assume that we have this circle representing the complete Indian population. So population. And now, in order to find out this answer, what you will do? So let's say this is you. This represents you. You will basically reach out to each and every individual. You will collect the data. So let's say the recharge done by person number 1. So let's say the recharge done by person number 1 is R1, then R2, then R3, and so on till R, let's say 150 crore. Now first of all, it is impossible, or not impossible, to near to impossible for you to collect the data of this much size, and it will be impossible for you to perform survey in such a large scale. So what is survey? Let's say if I'm having a group of people and I want to ask whether they prefer tea or coffee. So what I will do? I will perform a quick survey. So survey basically means I will go to each and every individual. So reach out to each and every individual, then ask them about their opinion. So ask the question, then collect the data, and finally we perform the estimation. So estimation means we calculate the average, minimum, maximum, whatsoever you want to calculate. This is the process of survey. Now if I have to perform the same thing on a population which consists of 150 plus crore people, don't you think for an individual like you it is near to impossible? Not impossible to near to impossible, and I would say it is impossible. Even for me or even for a government organization, it is impossible for anyone to perform a survey in such a large scale. Even if it is possible by a government organization, it will take a lot of time. lot of time, and it will take a lot of investment. Lot of investment means lots of money is required, lot of people is required, so lots of investment. Now, what is the better solution for this? We have already discussed about it. Solution is, I'll take a small sample. We call this as a random sample. Now I'll talk about what random sample is all about. But we take a small sample, we take random people. Let's say I have taken 1 lakh random people. 1 lakh random people from the population of 150 crore plus people. Now, as an individual, it is quite possible for you to perform survey on 1 lakh people. So you have performed survey, you calculated or you collected the data. So R1, R2 till R1 lakh. Then you took the average, and this is my sample average. Sample average. This is known as the statistic, sample statistic. Now using this, I will try to approximate my population parameter. So using sample statistic or sample mean, we will try to approximate the population parameter or population mean. And this is basically known as your inferential statistics. Inferential stats. Now before we talk about how to estimate the population parameter, let's try to quickly understand what is sampling and random sampling. So when we talk about sampling, it is basically the procedure of collecting few observation from a bigger subset, or you may say population. So I'm having a population. And now I want to collect a smaller sample, a smaller group of observations. This is known as a sample. Now this process is known as sampling. There is one very popular sampling technique which is known as random sampling. And this is a very important interview question. What is random sampling? Random sampling is nothing but assume that if I'm having a population having, let's say, numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So I'm having a population which is having 20 people, and the roll number of 20 peoples are written over here. Now if I have to select a random sample of 5 people, so select random sample of 5 people. So what we will do, we can select any 5 people, but according to the random sampling, the probability of selecting any observation is equal to 1 by n. So probability of selecting 1 is 1 divided by 20. Probability of selecting 2 is 1 divided by 20, and this is same for selecting any number is 1 divided by n, which basically means in simple random sampling there is no bias. We will just randomly select any observation from a population, and the probability of selecting any observation in my population is 1 divided by n, which is the same probability for every observation. So each observation in my data comes with same probability of getting selected into the sample. So here my sample can be 5, 9, 2, 7 and 10. Now why I have written 5, why I have written 9? I have just randomly selected these 5 numbers. So this is simple random sampling, and that is what I was talking about here, the simple random sample. Okay, now let's talk about how to perform estimation. In order to perform estimation, we use a particular algorithm which is known as the central limit theorem. Central limit theorem. Now what this theorem talks about? This theorem states that if I'm having a population, let's say this is a population of Indian people. Let's say I took one simple random sample of 1 lakh people. Now, when I calculated the average recharge amount for these 1 lakh people for sample number 1 came out to be, let's say, 250 rupees. For again, I took another sample number 2 of another 1 lakh people. The average came out to be, let's say, 220 rupees. I again took one more sample number 3. Again with 1 lakh random people, the average came out to be, let's say, 210 rupees. And like this, if I keep on doing, if I take enough simple random samples from my population and I quickly plot them in a particular histogram, I'll get a normal distribution like this. I'll get a normal distribution where the average of this normal distribution is my population average, and the standard deviation is given as sigma divided by root of n. So the first property of central limit theorem is the average of all sample average will be approximately equals to the population average. The second property is the standard deviation of the sampling distribution is given as sigma divided by root of n. Now these are the two properties of the central limit theorem, and using these two properties we can estimate the population range. Let's try to understand how we can estimate the population range. Let's say this is the question that is given to us. In a simple random sample of 50 adult women is obtained. So I have a simple random sample. This sample is having n is equal to 50 women, and when the red blood cell count was measured for them, this sample average came out to be 4.63. The population standard deviation is 0.54. Now let me go back, and I did not specify that this sigma represent population standard deviation, and this n represents the number of observations in the sample. So in this case, it would be 1 lakh. So central limit theorem states that the average of all these sample average. So I have taken multiple I have taken multiple samples from my population. These are my multiple samples. 1, 2, 3 and so on. And if I take the average of all these sample average, it will be closely equal to the population mean, a population average. And if I plot them, if I plot all these sample means in a distribution, in a histogram, it will closely resemble a normal distribution. And this distribution is known as the sampling distribution. This distribution is known as the sampling distribution. Why sampling distribution? Because we have obtained it using the sample means. So these are my sample means. Now, central limit theorem states that the average of all these sample mean will be closely equal to the population mean, and the standard deviation of the sampling distribution is sigma divided by root of n, where sigma is the population standard deviation and is the number of observations in the sample. Now this property is very important and very useful to estimate the population range. So I'm given with n as 50, my sigma population standard deviation is 0.54, my average sample mean is 4.63. Now I have to construct 95% confidence interval estimate. We already know that a sampling distribution follows a normal distribution. This is my sampling distribution for this particular event. So I know that my sampling distribution follows normal distribution. Let's say this is my mu, which is sample mean, and I want to estimate this range, lower value, upper value, in such a way that between these two I get 95% of my data. Now don't worry, I'm not rushing. Don't worry, I'll explain you everything. But this is my problem statement. I have to estimate the lower value and the upper value in such a way that between this I have 95% confidence. Right now we are using the word confidence, but as of now you can use the term that I need lower value and upper value in such a way that 95% data is between these two values. Now we already know this actually, that from the mean, if I go below 2 standard deviation and above 2 standard deviation, I can get 95% of my data using the second property of my normal distribution, right? But that is not exactly 2 standard deviation below the mean. I'll just tell you. Assume that this is my standard normal distribution, mean 0, and I have to find out the z value over here. What is the z value over here? And what is the z value over here? Z1 and Z2. And assume that between Z1 and Z2, the area is 95. So if the area is 95 between Z1 and Z2, this area, this black color area, what that will be? So the total sum of these two black color area will be 5%. So this will be 0.025 and this will be 0.025. How? So total is 1. Between these two data points Z1 and Z2, my area is 0.95. So I'll subtract. So I'm left with 0.05. Now since I'm having two shaded regions, I will divide it by 2. So I'm left with 0.025. So half is over here and half is over here. Now I have to find out the z value over here. So from here to here, the area under the curve is 0.025. Let's quickly use our z table. So 0.025, I have to go on the negative scale. 0.025 is over here, and this is minus 1.9 and 6. You can see it is not exactly 2, it is minus 1.96. So this point z1 is minus 1.96. Similarly, to find out z2, I have to go from here all the way up to here. So that will be 0.95. This is middle region plus 0.025. So that will be 0.975. So let's look at 0.975. So 0.975. 975 is over here. This is plus 1.9 and 6. So we have plus 1.96. Now we have the lower z value and upper z value. From the sample mean, to estimate population range or population parameter range. Why I am estimating a range? Because if my manager is asking me to find out average recharge made by the Indians, and if I'm using sample mean, I'm not 100% sure, right? So I cannot tell my manager that the sample mean was for let's say 280 rupees, because I have just analyzed one sample. I have just surveyed one sample. So I have to tell my manager with a range, that I can tell to my manager that, okay, sir, I don't know exact value, but I'm sure, I'm 90% confident, or I'm 95% confident that my population mean lies somewhere between these two values. So that is what we are trying to estimate. So if I go back to my question, to estimate the population parameter range in my sample mean, this sample mean, we will add and subtract the z times of sigma divided by root of n. What is z? So from this value, I am moving 1.96 standard deviation below the mean, 1.96 standard deviation above the mean of the standard deviation of my sample. So essentially what we are trying to do, from the mean, from the sample mean, we are just moving below and above. So to get this lower value and the upper value. So this is my mean. In order to get 95% confidence, I will move minus 1.96 standard deviation below plus 1.96 standard deviation above the mean, and that will get me the population range. So mean is 4.63 plus minus 1.96, standard deviation is 0.54 divided by sigma of root 50. If I solve this, 4.63 plus minus, so this will come out to be 0.149, and the range would be 4.481, 4.779. What is the meaning of this? This basically means that there are 95% chances that the actual population mean would lie somewhere between 4.481 to 4.779. So it was asking me construct 95% confidence interval estimate for the mean of red blood cell count of the adults. So right now 50 adult women were taken and their sample mean was 4.63. But if we talk about the complete population of adult women, then this range states that there are 95% chances that the red blood cell count of the complete adult woman population would lie between 4.481 microliters to 4.779 microliters. That is what this range is. Let's look at one more question, and then it will clear all your doubts and it will be very clear to all of you. So the question says you want to rent an unfurnished one-bedroom apartment in New York City. The mean monthly rent of random sample of 60 apartment advertised in some website came out to be $100. So what you did, you were trying to estimate what is going to be the average one-bedroom cost or average one-bedroom rent in New York City. So what you did, you Googled and you searched through some website. You sampled 60 apartments in the same city. So 60 apartments, my N is 60. And after looking at all the rent, the average of this sample came out to be $1,000. And the standard deviation was, you assumed that the population standard deviation to be $200. So this is just an assumption. Population standard deviation is $200. This is population. Now we have to construct 95% confidence interval. Again, for 95%, we have already calculated the z values. So the z values is minus 1.96 plus 1.96. So we will just apply the formula mean plus minus z times of sigma divided by root of n. Mean is 1000 plus minus 1.96. Sigma is 200 divided by root of 60. And if I just quickly solve this, it will came out to be 949,1050, which basically mean there are 95% chances that the actual rent of one bedroom apartment in New York City would be somewhere between $949 to $1050. And this is what the application of inferential statistics is. I hope you guys are able to connect all the dots and able to understand how we have arrived to this particular point. Now this concludes our discussion in inferential statistics. I hope this module was informative and really useful for all of you. If you like this video, share it with your friends, give this video a big thumbs up, and don't forget to subscribe to our Scalars YouTube channel.